let's do this. Okay. Okay, today. Okay, so now we go through our new chapter, mathematical modeling. Okay, so from the lesson outcomes should be student be able to derive a mathematical model, meaning you have to derive the mathematical model in terms of transfer function. Okay, you have this topic also you have to define the transfer function, but you have to use reduction technique. Okay, you have to use block diagram reduction technique to define the transfer function. Okay, right? Okay, what is a mathematical model? What is a maths model? Okay, in order to understand the behavior of the system, we have to define the maths model. Okay, before we want to understand the behavior of the system, what is the behavior of the system? We want to define the behavior. Is it we want to define whether the system is a stable or unstable or marginally stable, meaning marginally or critically. Okay, actually we have three type of behavior of a system: stable, unstable, and critically stable. Okay, before we want to understand the behavior of the system, we have to define the mathematical model first, meaning we have to represent our maths model in terms of transfer function. Okay. Okay, the next one, maths model are equation which describe the relationship between the input and output. Okay, that meaning, what's the meaning about relationship between input and output? Meaning this is a transfer function. Okay, transfer function is a relationship between input and output of a system, right? Okay, and then the third one, the basic for any mathematical model is provided by the fundamental physical law that govern the behavior of the system, meaning fundamental physical law. Okay, from this chapter, what type of the physical or fundamental physical law we will be going to use? For electrical system, uh, we will use Ohm's law. Okay, hopefully everybody know what is Ohm's law. Okay, and then for mechanical system, okay, type of physical will be covered to one electrical system. Okay, another one is a mechanical system, and mechanical mechanical we have two type of system. One is a linear mechanical system, the second one is a rotational mechanical system. Okay, so how to derive the maths model from the mechanical system? We use Newton's law. Okay, guys, you know what is Newton's law? Who can give the answer? What is Newton's law? What is a Newton's law? What's a formula for Newton's law? Guys, can share? What is a Newton's law?
Madam, that Newton's law has three laws, right?
Newton's law. What is a Newton's law? What's the formula for Newton's law?
Mass times acceleration.
Force equal to
Mass
multiply with the acceleration.
acceleration.
Yeah, good. Okay, thank you. Okay, that's a Newton's law. Okay, that's a physical law. We will use during we analyze the mechanical system. Okay. Now, first we covered on the electrical system. So this is just an introduction, basic element of electrical system we're going to use. Okay, the RLC. Okay, we will the RLC circuit, meaning this is from the three slide. I just scan through and show you the basic component we're going to use. Okay, the resistor, the inductor, and the capacitor. Okay, this means we from this we will analyze RLC circuit. Okay, from this table, okay, you can see table 2.3. Okay, this table you also can refer from our textbook. Okay, so this topic or this part control system uh, textbook you can refer normal nice textbook. Okay, I think you can get the ebooks, okay, from the island. If you can log in, you can get the ebook for that reference textbook. Okay, you can get the textbook from there, from the island. Okay, so everybody, you can see from table 2.3. Okay, this is show the relationship between the voltage current, voltage charge, and impedance relationship for capacitor, resistor, and inductor. Okay, but for this one, this is we put aside. So the component will be covered is this type of component, capacitor, resistor, inductor. Okay, from here you can see the relationship between voltage and current for the capacitor, resistor, inductor, and etc. Okay, and also the current, relationship between current and voltage. This is a relationship between voltage and charge, and the last one is an impedance. Okay, the impedance we label is Z, okay, or Z, and then V over I. Okay, this is how to define the impedance. For the capacitor, impedance is 1 over CS. Resistor impedance is R, and the inductor, the impedance for inductor is LS. Okay. After this, we can share what you can see from the analysis of the circuit, and then this table 2.3 we will going to use during we analyze the RLC circuit. Okay. Okay. Let's see example number 1. I think everybody is quite familiar with this circuit or electrical circuit. Okay. This is a RC. Okay. The two-port network show in figure has a VI. VI is our input voltage and V0 as the output voltage. Okay, so you have to define the transfer function, meaning transfer function is a ratio between output over input. Okay, this is the ratio. We want to define output over input, meaning your V0 over Vi. So we want to define this transfer function in terms of S domain. Okay, we want to define this equal to what? Okay, we want to define the relationship between output and input. Okay, so I share to you the solution for example 1. Okay, so you have to derive using what? So you have to derive using Ohm's law. Okay, Ohm's law. What's the equation for Ohm's law? You can give me, guys, what is equation for Ohm's law?
B is equals to IR.
Okay. Okay, this is our Ohm's law. Okay, so from the next slide, okay, I list down the input. Input is our applied voltage. Output is our, this one. Okay, output is our output voltage. Okay, so first you have to derive this one. Okay, this. Okay, we have to derive the voltage. Is it total of voltage for that circuit? Okay, so VI equal to, this is our current. Okay, this is your current. So first you have to derive total of voltage here. Okay, so meanings VI equal to R multiplied with the I total, meaning IT plus 1 over C for this one, meaning VR, and this is your VC. Okay, in terms of, now we want to show the relationship between voltage and current through the resistor and through the capacitor. Okay, so this equation, okay, this equation you can see from our table. Okay, this one, is it? So now I want to show the relationship between voltage and current. We want to define VR, we want to define VC, we want to define total of voltage here. Okay, meanings we input equal to VR plus what? Plus VC, right? Okay, meanings the VI, oh sorry. So your, actually we want to define VI equal to VR plus VC. Okay, from here we derive. Okay, so meaning VR, what is a VR? We use this table. We use this relationship between voltage and current. Okay, so meaning how to get the VR is a Ri, and then how to derive voltage capacitor. Voltage capacitor is this one. Okay, voltage through the capacitor is I over C integral IT. Okay. Okay, how about this one? How about V naught? Is it our output voltage is equal to our voltage capacitor? Is it V naught equal to VC? Guys, from the circuit.
Yes.
Okay, very good. Okay,
Yes.
your V naught equal to VC, right? Okay. Okay, so this is consider our equation number 1, and this is our equation number 2. Okay, I want to show equation 1 is I want to show the total of the voltage inside the circuit. Okay, but voltage capacitor equal to V naught. Okay, so we want to define what's the transfer function. We want to define the transfer function V naught over Vi. So the voltage capacitor we have to derive in terms of V naught. Okay, we want to, in our transfer function, we want to define V naught. Okay, so you have to simplify your voltage capacitor into V naught. Okay, so let me see the next. Let me see this one. Okay, taking Laplace transform of both equation, considering, okay, we consider the initial condition to 0. Okay, so meanings when we're taking Laplace transform, we can get this equation. Okay, the first equation, we taking Laplace transform, we can get the third one. Okay, and second equation, when we take it over Laplace transform, we can get equation number 4. Okay, so you have to rearrange both equation. Okay, so you have to rearrange the equation, meanings of what? So this one, we rearrange the third equation, we rearrange fourth equation to get Vi equal to I R plus 1 over S, and then the fourth equation we derive, you can get CS V naught equal to I, and then from there you substitute meanings. Let's say I make it, this is equation 5, okay, and this one is equation 6. Okay, so the last step, you have to substitute current from equation 5 into equation number 6. So we can get this one. Okay? So we substitute current, meaning current from equation 5 into equation number 6. Okay? So you can get this one. We can get equation number 7. Okay. From here, you have to rearrange equation 7 to get equation number 8. Meanings, we want to define the transfer function V naught. So meaning, you have to rearrange the equation until you can get equation number 8. Okay, and then from number 8, so you can derive your transfer function. Okay, number 9 is your, number 9 is the transfer function. Okay, and then from equation number 9, we rearrange to rearrange, meaning we want to take it as, okay, right? So meaning you have to divide the upper equation, meaning you have to divide both with the RC, okay? So you can get equation number 10. Okay, this is, we want to, this is the transfer function we want to solve. Okay, equation number 10. Okay, this is the transfer function V naught over Vi. Okay, like this. Okay, so meaning we want to define V naught over Vi. Okay, this is the V naught over Vi. So we're capable to define this first RC circuit. Okay, so any question from this example? Is it quite simple, right? Because our example only one loop. Okay, we want to show the relationship between output and input from this two-port network. Okay, so how, class? Any question so far? So far so good?
So far, so good, madam.
Okay,
Okay,
so I
madam.
think everybody is quite familiar with the electrical circuit, right? Okay, let me see. Second example. how to solve. This is a second example, meaning this is a RLC circuit. Before this is a RC circuit, okay. From here is a RLC circuit. Okay, so you have to find the transfer function relating the capacitor voltage, meaning is a VC, a capacitor voltage, to the input voltage. So meaning we have to define what is your output. Output is your voltage capacitor over your input. Okay, so you have to define this relationship, voltage capacitor, or sorry, capacitor voltage to input voltage. We have to define this transfer function from the RLC circuit. Okay, so meaning also same, you have to define the total of resistance, sorry, the total of voltage from this RLC circuit. Okay, so you can see from the equation number 1. Oops. Okay, so how to define from here, how to define the voltage around the loop. Okay, so we want to define the summing or the total of the voltage around the loop, and we assume zero initial condition. So meaning during we analyze the circuit, we assume zero initial condition. Okay, so meanings integration difference. So what's equation you can derive from the summing of voltage around the loops? So meanings our V in supposedly equal to VL plus VR and plus VC, right? Okay, and then from here we derive based on differential equation. So you can get equation number 1. Okay, how to derive the inductor voltage. Okay, in terms of currents given. So let me check from the table 2.3. Okay, the relationship voltage and current. So we define from here. Okay. So we define this. We see the relationship between voltage and current for the inductor. So for the inductor, this one. Okay. And then for the resistor, and then this is for the capacitor. Okay. We use this table, okay, to derive the equation. Okay. To derive the equation. So meaning voltage through the inductor, this one, okay, L di over dt. This is, let me see, this is a VL plus VR plus VC equal to total of voltage. Okay, sorry, this is our V total. Okay, that's from equation 1. Okay, now the second step, you change the variable from current into charge, meaning using this one. We replace equation 1, meaning we change current into charge. So you can get this one. I current equal to dqt over dt. Okay, so we can get the second equation. All the current we change to charge. Okay, so we can get the second equation. Okay, still can follow. Hopefully you can follow. Okay, right. Okay, now, so from equation 2, we show the form voltage charge relationship. Okay, from the voltage charge relationship from equation 3. Okay, here. Okay, this is I want to show you the voltage charge relationship. Okay, Q equal to what? Equal to C VC Q equal to C VC. So meaning from this one, from this table, where is our charge? For capacitor, 1 over C. Where is just now? Q equal to voltage charge relationship. Voltage charge relationship. Okay, this one. From this okay, this is a relationship between voltage and charge. We use this table to uh, to show the voltage charge relationship, so we can get equation number 3. Okay, so we substitute equation 3 into 2. Okay, so you can get this one. Okay, let's say I'm level equation number 4. Okay, this is equation number 4, right? Okay. So, once you get your equation number 4, so you can see from here, this is our VC. Okay, this is our voltage capacitor based on relationship between charge and voltage. Okay, from here we can get VC because we want to define the transfer function. What is our transfer function just now? We want to define the transfer function in terms of voltage capacitor over our input. Okay, so meaning we already from our derivation we can get our voltage capacitor here. Okay, and then once after substituting 3 into 2, so you can get equation number 4, and then from there we taking the Laplace transform. Okay, and then we rearrange we simplify the equation number 4, so we can get equation number 5. Okay, and then so from equation number 5, so you can solve the transfer function. Okay, you can get VC over V, and then you can obtain this one. This is the transfer function we want to define from this circuit. Okay, class, are you with me?
Yes.
Okay, okay, very good. Okay, let me check. Okay, the next slide. The next slide is equivalent. Let's say this circuit, okay, RLC circuit. I want to show the equivalent transform the impedance. Okay, meaning you can see equivalent from that slide, equivalent transform impedance. Okay, technique for simplifying the solution. Okay, take the Laplace transform of the equation in the voltage current column. Maksudnya pula. So meaning we take the Laplace transform of the equation in the voltage current relationship from the table 2.3, and then assuming our condition on the zero initial condition, okay? And then we can get the impedance transfer function Z equal to voltage over current, okay? So I put the notes there from the impedance equation, this one. Okay, similar to definition of resistance, meaning ratio of voltage to current. Okay, how to define the impedance, right? So from that table 2.3, you can see from this table, okay, capacitor. What is the impedance for the capacitor? It's a 1 over CS. Okay, this is how to define the voltage. Voltage, what's the impedance for the capacitor? Okay, impedance for voltage is this one. You can see from the table, and the voltage, the impedance of resistor is Ri, and then for the inductor is LSI. Okay, that's the impedance for capacitor, resistor, inductor. Okay, this impedance we can refer from table 2.3. Okay, from the previous slide. Okay, so how to see the meanings? We transform from the transform circuit. Okay, transform circuit, we redraw the original network showing all time variables such as voltage current and voltage capacitor as Laplace transform. Okay, meaning as Laplace transform, meaning V in term of S, okay, instead of time T, okay. This one is based on time. This is in term of as a Laplace transform in term of S domain, okay. And then step number 2, replace the component value with their impedance value. Okay, that's meaning the easy way how to define the transfer function when we use equivalent transform impedance circuit. Okay. Okay, let's say this is skip. Okay, let's see example number 3. This is similar with our example number 1 just now, but this one we analyze based on total impedance. Okay, the total impedance. Okay, hold on. See.
Sesi talk is a stop organized by Mas Medi. Ini adalah session yang keempat ya. Keempat, kita ada 5 talk. Ini yang keempat.
Okay. Can you see the equivalent impedance circuit? Okay. So from here, from this circuit, example 3 is the same with the example 1, but this one is we solve the circuit based on the impedance. Okay, we solve based on the total of impedance. Okay, So you can see from this example, equation 1. Okay, let's say from the equation 1 is this is a total of voltage. We want to find out the total of impedance. Meaning we want to define the total of voltage. Meaning this is total of voltage equal to VR plus what? It's a VC, right? Okay, so meaning we derive the equation. You can get what's the total of voltage here? Meaning V input equal to VR plus VC, and then you have to define this one. Impedance. What's the impedance for VR? Okay, meaning impedance of VR in terms of S domain, right? So we can get from this equation 1, okay, VI in terms of S domain, okay, equal to R IS plus V naught. That's equation 1. But what is some function you want to define? You want to define this sum function. Okay, you want to define V naught over VI. But you have to know what's a V naught. V naught equal to voltage capacitor, right? Okay, V naught equal to voltage capacitor. V output equal to capacitor voltage. Okay, so meaning we derive equation number 2. Okay, meaning we derive this one. So we derive V naught equal to, this is the impedance for capacitor. Okay, this is the impedance for capacitor. Is it? See, from this table, from table 2.3, what's the impedance for capacitor? Okay, this is capacitor. This is the impedance. Impedance for capacitor, impedance for resistor, and impedance for inductor. Okay, you use this table to analyze the circuit. Okay. Okay, this one. Come back here. So, V naught equal to capacitor voltage. But, what's a V naught? What's a voltage capacitor? So, meaning voltage capacitor is this one. Okay, this is a voltage capacitor. So you can get, okay, current equal to C S multiplied with output voltage. Okay, so from equation 1 and 2, okay, so you substitute current into equation 1, 3 into equation, is it correct? We substitute current into equation 1, meaning we substitute 3 into equation 1. Okay, so we can get equation 4 and then from 5. Okay, from equation 5, we rearrange to get the transfer function. So we can get this function. Okay, guys, you can follow.
Yes.
Yes, madam.
Okay. Okay, very good. Okay, how about example number 4? Example number 4, we want to define output voltage per input voltage. Okay. V naught over Vi. So that's similar with the previous also. That's similar with the previous circuit. Okay, but I just redesign the C and R. Okay, I just replace C and R. Okay, from here, what's the time function? The time function is we want to define the transfer function output voltage over input voltage. Okay, so first step, we have to define the total of voltage around the loop. Okay, so meaning input voltage equal to capacitor voltage plus resistor voltage, is it? Okay, from here, we define what is the impedance for capacitor and relationship between capacitor voltage, and then what's the impedance for resistor. Okay. So is it our VR equal to V naught?
Yes.
Our resistor voltage equal to output voltage, right? Okay, right.
Yes.
Equation 1. Okay, so equation 1, we can get this is our voltage input voltage equal to is your capacitor voltage, right? Plus V naught or VR, okay? So meaning you can put VR also, but after like this, let's say if you want to put VR, so here you can get RIS, right? If you want to put VR. Okay. So from there, let's say for equation 1, we finish equation 1. Okay, but your VR equal to V naught. Okay, from here, your V naught equal to resistor voltage. Okay, so we derive equation number 2, meaning your V naught output voltage equal to your resistor voltage. So we can get equation 2. And then, so we simplify equation number 2, so we can get equation number 3. Okay, so we can get current here. So substitute current into what? Into equation what? We substitute current from equation 3, substitute into equation number 1. Okay. So you can get this equation number 4. Okay. I change this one nanti make it you confused. Okay. Right. So we can get equation number 4 after we substitute current into equation number 1. Okay, and then you rearrange the equation until you get equation 5. Okay, and from there you simplify equation number 5, and then we can get our transfer function. Okay, this much simpler compare with the first step. With the first, how to analyze the circuit based on what? Based on the difference, what? The integral differential based on the DE, okay? Based on the differential equation, meaning in terms of time domain, okay? Meanings we have two method, okay, to analyze the circuit, okay, before you define the transfer function. Okay, we use the DE, or another one we use the impedance. Okay, which one the quite simple? Using the differential equation to analyze the circuit, or using the impedance? Which one the much easier for you guys? The first method or the second method? Or hopefully you can use both for practice, right? Okay, at least you have two method to verify how to define how to define what the time function for that circuit. Okay, hopefully both method you can yeah, hopefully you will be familiar with the two type of analyze. Okay, so this one is an example 5. Let's say we revisit our example number 2. Okay, this is the solution. Okay, solution from that circuit. Okay, from here, okay, let's say this from here, this is the impedance. Okay, the equivalent impedance circuit, meaning this is for the resistor, impedance for resistor, and this is the impedance for the capacitor. Okay, so meaning the Vs equal to VL plus VR plus VC, right? Okay, and then okay, voltage, the inductor voltage equal to Ls multiply with the current plus, how about the impedance for resistor? R multiply with the current, and then how about the VC? The impedance for capacitor is the 1 over CS multiply with the current. Okay, similar like this, right? Okay, from here you can get this one. Okay, we use a mass equation, so meaning writing a mass equation using the impedance. Okay, as we would use a resistor value in a purely resistive circuit and etc. Okay, so meaning from here, from just now, from this one, we rearrange. Okay, we rearrange for the current. Okay, we rearrange the current so we can get this equation. Okay, we can get this one. Wait, let's say this is I'm labeled with equation 2. Just now equation number 1. Okay. Now solving current over voltage. So meaning we solving our current over voltage, so you can get equation number 3. But okay, so you can read from here. But the voltage across the capacitor is the product of the current and the impedance of the capacitor. So, what is the voltage capacitor voltage? This is the capacitor voltage. Okay, so we have to just now voltage capacitor current. What is from here, current. Okay, how to get this equation? How to get this some function? Capacitor voltage over voltage, meaning this is consider our input voltage. Okay, how to get this kind of the transfer function? Who can share? How to get the VC over VI from equation 3? Is it we change current? Is it possible we change this current with this one? Is it possible? So meaning from here, what is the current? Current. What's the current from this equation? Current equal to is it like this, guys? Current, is it true? Current, and then is it correct, this equation? Is it correct, this equation? Betul ke tak?
Yes, madam.
Okay, betul kan? Okay, so jadi you you replace equation number, let's say I make it this equation number 4. Okay, we simplify to get the current, and then you substitute the current into this one. Okay, you substitute current into this equation. Okay, so we can get this transfer function. Okay, I equal to CSVC, and then we bring back CS on the right. Okay, so meaning we simplify after you substitute current into equation number 3. So you simplify until you can get this transfer function. Okay, boleh follow tak? Boleh ikut ke?
Boleh.
Okay, so this is saya pass yang ni. Okay, so meaning we finished our what? We finish our electrical system. Okay, how to analyze or how to define the transfer function from the electrical system. Okay, so far, any question? Any question so far, class? Or so far so good?
Done. So far, so good.
So far, so good.
Okay, so far so good. Okay, right? So hopefully this table you can which table? Table 2.3. Okay, the table 2.3 is we will going to use during our circuit analysis. Okay, the relationship between voltage current, voltage charge, and the impedance. Okay, the impedance for capacitor, resistor, and inductor. Okay, normally we for the electrical circuit analysis we will dealing with these three components: capacitor, resistor, and inductor. Okay, we always dealing with this type of the component RLC circuit or RC or RL or CR. Okay. Okay, class, give me 5 minutes to define or to find out the exercise for you. Okay. We take 5.